Hi, I'm Matthew McGilvary, and this is our study, the empirical study of simplex algorithm using classic pivot rules. Now, the simplex algorithm was invented by George Dantzig in the late 1940s during his work in the United States Air Force. It was used to solve logistical problems, but it was soon discovered the simplex algorithm could be used to solve many problems that could be considered as how to allocate a finite number of resources in the most efficient way possible. Some examples you'd see the simplex used in everyday life are in manufacturing, shipping, and in budget and portfolio management, to name a few. Now, despite its popularity, there are some questions about the efficiency of the algorithm. There are theoretical cases where it takes exponential time to complete the problem, though its average case time is polynomial. Now, the simplex algorithm could be represented geometrically by this structure right here, is known as a polytope. And you could think as it's reaching the most efficient point possible while walking along the edges and vertices of this polytope. Now, the simplex algorithm does not do this just blindly. It uses what's known as a pivot rule to decide which vertex to move to at each iteration in the process. You can see in this picture right here that in our project, we use Dantzig's rule, the greatest increase rule, and Bland's rule. So here, if we wanted our objectives to get as high as possible in this polytope, Dantzig's rule would move from this black point to this red point, while the greatest increase would move from this black point to this green point. So it's not determined how it's going to turn out in the beginning, and you have to go through the pivot rules. So therefore, you have to use empirical studies to understand the behavior of the simplex algorithm. So for our project, we created these polytopes using spheres and ellipsoids for the third, fourth, and fifth dimension. You can see that right here with this sphere. We then picked points along the surface randomly to create a polytope. We then we used a mathematical software known as Polymake to do this. And then we used the simplex algorithm to create paths along that polytope that went from a minimum to a maximum. You can see here is a spherical polytope case of red, our different pivot rules and the shortest path, and then for an ellipsoidal polytope. And to do this, we had to use computations on UNC's longleaf data cluster for parallel computing. It took approximately 500 CPU days to complete the computations. Handing it over to Juan now.
Thank you. So on to our results. We define R stability, which is a sensitivity measure of optimal pivot rule performance due to change in the ellipsoid's minor axis R in our dimension 3. At a given visited vertex, called the simplex algorithm's path P1 and the shortest path to the optimal vertex P2. For a given pivot rule and for each minor axis length R, construct the curve IRC, where C is the percent complete of the simplex algorithm, and IRC is the probability that the lengths of P1 and P2 are equal. Now, say H is the set of all curves IR, while all are. We define R stability as the following formula, but you could just take it as the largest area formed between any two curves in H. In other words, R stability captures the greatest shift an IR curve takes from one minor axis length to another. So our two pictures following, to the left is a collection of all IR curves due to the greatest increase rule, whose path more likely will be equal in length to the shortest path as we approach the optimal vertex, and this follows for the other rules as well. Maximal shifting occurs here than the other rules, so its R stability is also the lowest. To the right is a collection of all I2/10th curves for all rules. Note greatest increase is the quickest, denoted by the green curve, to increase likelihood of shortest path length, then Dantzig, then Bland. Onto the average Euclidean distance from the ellipsoidal center. To the left, we have Bland's rule, and all others follow the same dynamics. The average path will walk across the flat face of the polytope, moving closer as R decreases. To the right, for R equaling 1/10, and for any sufficiently small R really, an average Bland's rule will be farthest from the center than all the others, denoted by the blue curve. Lastly, we go on to the pivot rule's path with moving lower bound from the center. To the left, we have Dantzig's rule and all others exhibiting similar behavior. The likelihood of its path to remain a certain distance d from the center decreases with increase in d and decrease in r. And to the right, for sufficiently large d, Dantzig's rule gives the highest probability that we can have something this far. And to conclude, the greatest increase rule yields greatest R stability. On average, all considered rules' paths are not on the edge of the polytope. However, Bland's rule becomes the farthest from the center on average as the minor axis decreases, and Dantzig's rule for sufficiently large distance from the center yields the highest probability that the path stays at least that far of a distance from the center. For future directions, we like to add more inequalities, more radii, higher dimensions, and different pivot rules. And we like to thank our acknowledgements as seen below.